My warm greetings to you. I welcome you to my presentation on voltage stability part 2. First, let me summarize the topics discussed in my part 1 presentation. I discussed about the importance of studying voltage stability. Also, I discussed about the definitions of voltage stability, voltage instability, voltage collapse, and voltage security. In this presentation, I will be discussing about how the voltage stability is classified and what are the various factors that causes voltage instability. I will discuss about previous cases of voltage collapse incidences and physical relation indicating dependency of voltage on reactive power flow in my next presentation. First, let me explain how voltage stability is classified. There are two ways of classifying voltage stability. Based on time frame, voltage stability can be classified as short-term and long-term voltage stability. Based on nature of disturbance which is occurring in the power system, voltage stability can be classified as small disturbance voltage stability and large disturbance voltage stability. Now let us discuss what is short-term voltage stability. How do we define short-term voltage stability? It involves the dynamics of fast-acting components. What are the examples for these fast-acting components? Let me give few examples. Automatic voltage regulators, excitation systems, turbine and governor dynamics, induction motors, electronically controlled loads, and HVDC converters. How long this short-term dynamics last? It lasts only for a few seconds. How do we analyze this short-term voltage stability? It requires solution of appropriate system differential equations. Examples of short-term or transient voltage instability can be found in the instability caused by rotor angle imbalance or loss of synchronism. Next, we will move on to the definition of long-term voltage stability. Long-term voltage stability involves the dynamics of slow-acting equipment. Examples are tap-changing transformers, thermostatically controlled loads, and generator current limiters. This time frame is for a few minutes to tens of minutes. It is mainly due to the large electrical distance between the generator and the load. Timely application of reactive power compensation or load shedding may prevent this type of voltage instability. I hope you are able to understand the definitions of short-term as well as long-term voltage stability. Let us move on to the classification of voltage stability based on disturbance which is occurring in the power system. We can classify voltage stability as small disturbance voltage stability and large disturbance voltage stability. Now let us discuss about the definition of small disturbance voltage stability. It is defined as the system's ability to maintain the steady voltages when subjected to small disturbances such as incremental changes in system load. This refers to gradual increase in system load. This form of stability is influenced by the characteristics of loads, continuous controls, and discrete controls at a given instant of time. Now, let us define large disturbance voltage stability. It refers to the system's ability to maintain steady voltages following large disturbances, such as system faults, loss of generation, or circuit contingencies. This ability is determined by the system and load characteristics and the interactions of both continuous and discrete controls and production. The study period of interest may extend from a few seconds to tens of minutes. Now let me explain the various factors which are responsible or which are causes for voltage instability. First and foremost important reason for voltage instability is the inability of power system to meet the reactive power demand. When I say that power system is voltage stable, it means that bus voltages are steady and within acceptable limits. That is, there is neither low voltage nor high voltage. Reactive power balance should continuously be maintained for achieving the steady voltages at all the buses. Shortage of reactive power at heavily load condition may result in low voltage, and surplus of reactive power due to light load condition will result in over voltage. Thus, reactive power imbalance will result in voltage instability. Hence, we can comment that reactive power plays a vital role in maintaining voltage stability in the power system. The next factor is increase in load or system changes. Voltage instability is driven by load. So it is otherwise called as load stability because load determines the voltage stability. Inherent weakness of power system is also one of the factors causing voltage instability. Increased electrical distance between generation and load causes large voltage drop, because of which voltage instability results. Tripping of transmission or generation equipment is also responsible for voltage instability. Heavy or over compensation of sun compensation will result in over voltage. Improper function of voltage control devices like AVR, load, load tap changing transformers are also responsible for voltage instability. The other factors are transmission network characteristics and load characteristics. These are the various factors which are responsible for voltage instability. In this slide, you could see few of the reference books which you can refer for further reference. Also, I have listed out my publications on voltage stability for your kind reference. I request you all to go through it. Thank you. I'll see you in the next video.